And start with you and ask you a little bit about heterogeneous integration. You should probably define it a little bit for some of our audience, the moving of parts together, but tell us why it's so important and what it gives us.
So I have 2 hours to answer that question, right? I do teach a whole semester worth of material on this, but I'll make it very brief and to the point. Okay, so heterogeneous integration is really a form of advanced packaging that is just very aggressive in its ability to integrate chips of various functions at very high densities and low energies. Why is it important? So I think there's a few answers to why it's important. And there are different answers, but they're all true, and collectively they form the big picture. So the first is that historically when we build electronic systems, we package chips separately. So you'll have a CPU maybe in one package, the memory in another package, and they have to communicate together across the motherboard. That distance is many, many inches, right? Unfortunately, electrical interconnects don't do so well at long distances. And so the way to solve that problem is to try to bring chips closer together so that you reduce the distance between them. Thereby, you get benefits on energy, you get benefits on bandwidth, and you get benefits on bandwidth density. Okay? And so there was a study done actually in the US some 20 years ago, and it was looking at the environmental impact of data centers. And one of the punchlines that came out that was very shocking at the time is that when you look at a whole data center, so much energy just gets spent in sending data back and forth. So if you can eliminate that, that's a significant chunk. Okay, so that was really point number one. Point number two is, why is heterogeneous integration so important? Silicon technology is changing, okay? So I already made a comment about Gordon Moore predicting that it's going to be cost efficient, but let me put some color behind this. There was a paper published by the CEO of Samsung a few years ago, and what he showed was, to me, remarkable. And what he showed is that if I take a 3-nanometer silicon chip of 450 millimeters squared, okay? So suppose I have a single chip, 450 millimeters squared at 3 nanometer. He showed that if I break that chip into 2 halves and I reconnect at the package level, you can save 50% in silicon cost.
Say that again, you can save 50%?
Almost 50% in silicon cost. And so the yield of these smaller chips at leading edge nodes is better, right, than a larger chip. Another part to the story is that in the silicon, right, at the wafer level, your reticle size is limited. You can only build a chip of certain size. Lithography cost, et cetera, et cetera. The punchline that AMD published is that they showed that we can build more powerful CPUs and GPUs by aggregating a lot more cores at the package than what monolithic integration can do. And then, if I may add one more comment, which is, we all talk about packaging problem. And yes, we have a packaging problem, and thankfully, there's a lot of smart people in the world that are solving it. This is not the first time the industry faced a packaging problem. In the 1950s, people were building electronic circuits using discrete components, meaning single transistor here, single transistor here, single transistor here, and you would have to hand solder these transistors together. This is what people refer to as the tyranny of numbers, which is that as circuits got more complex and you needed more and more components, it was becoming very difficult to do this hand soldering business. So people realized, in order to build more complex circuit, more advanced circuit, you got to find a solution. What was the invention that solved this first packaging problem? The integrated circuit. The integrated circuit that we're discussing was invented to solve a packaging problem. Circle back to today. We're living in another packaging problem. One can only wonder what transformative new technologies will come out that may transform really how we think about building semiconductors going forward. So that was point number 3, and I'll stop here.
Thank you. So